Now we're going to look at another model of computation, which at first, to most people's eyes, seems rather strange. It's a little bit abstract, but it's very beautiful and I want to share it with you. And it was founded primarily by Alonzo Church, another logician of the 20th century. It is built entirely on strings of symbols and substituting symbols with other strings, and just doing that over and over, kind of unfolding the string until it reaches some final value. So here's how it works. There's a little thing in here, a little symbol called lambda. Indeed, this is called the lambda calculus. Lambda x means every time you see the symbol x, I want you to replace it with a copy of the following string, the string after this expression. So let's give an example. Lambda x dot xx means take the next string you see and make two copies of it. Substitute it for each x in the string xx. So if I put in the string a, it will produce AA. See how that works? We can also apply this to longer strings. So if I take lambda x dot xx and apply it to the string AB, I get the string ABAB. Now, it's kind of important here to keep track of the parentheses so that we know if we follow something with multiple strings, what to do first and how to break it up. So let me explain. I can also form, as it were, a function of two variables. So think about the string lambda xy dot xyx. Now the xy gives this string kind of two places to plug things in, two variables with which we can substitute in some string. So let's apply this to the following two strings, AB with parentheses around it, and then C. What does the lambda calculus do? Well, we start with the first thing in the lambda, the x, and we take the first string, AB, and plug that in for all the copies of x. So that gives us AB, Y, AB, but we still have that lambda y. It's still another port waiting to have something plugged in. We continue and plug in the one character string C in for that copy of y, and that gives us our final answer, AB, C, AB. And now we're done. So sometimes when you complete this process, there might be still a few unplugged variables hanging out at that lambda, or sometimes you've substituted in a string for every variable in the lambda, and you get something which isn't really a function anymore, it's just a string. Okay, good. So there's a beautiful fact about the lambda calculus, which is there's no distinction between functions and the data that functions act on. Now, this is pretty profound. So think about standard mathematics. There are numbers, things like x, y, and z. There are functions that take those numbers and usually produce additional numbers. F of x comma y is x plus y or x times y or whatever. Then there are other things like the derivative. What is the derivative? Well, it's something which takes a function and produces a new function. But we would never apply a function to itself. Or what does it mean to apply a function to the act of taking the derivative, if you know what I mean? In other words, standard mathematics has this kind of rigid hierarchy. There are numbers down here, functions act on those, some higher level things like the derivative act on functions and so on, but there are no loops here. But in the lambda calculus, everything is on an equal footing. So for instance, consider the following function. Lambda fx returns f of x. Well, suppose that I put in some function g to this. It's just going to return the function which applies g twice. Do you know what I'm saying? This is a higher order function that takes a function as input and turns it into the function which does that function twice. So it's a function which acts on other functions, but you could also apply it to itself. It's just another string that you could plug into itself. So there is a style of programming languages that take this attitude. Lisp is the most basic, and on top of Lisp are built other things like Scheme and Haskell. The innards of Mathematica, the so-called Wolfram language, is really just substituting symbols and strings for other symbols and strings. That's all it ever does. By the way, if you're an advanced Python programmer, you know that Python also has lambda, so it can do lambda-like things. But this fact that functions and data are all on the same footing inspired people like Walter Fontana, who's now at the Harvard School for the Harvard Department of System Biology, and who was a postdoc at the Santa Fe Institute, to use the lambda calculus as a model of chemistry. Because in chemistry, well, enzymes have functional roles. They can act on other proteins and do things to them, but enzymes can act on other enzymes as well. Everything is just a chemical that binds with other chemicals and can join two of them or break one apart or modify it. And some people believe that in the early days of the evolution of life, we had this world where everything was just RNA, and RNA was acting both to store information like data, but RNA can also fold up the same way proteins can, and form what we call ribozymes, strings of RNA that can act on other strings of RNA, so that the same stuff, the RNA, was acting both as the data and as the program. So this is another way in which computer science differs from many other branches of mathematics. A program is a thing you can run, which does stuff to data and produces an output. But a program is also data itself. It's just a text file, which you can modify with a text editor or hand to a compiler, so you can give programs other programs as input. You can even give programs themselves as input, and this will lead to interesting places. All right, good. So the lambda calculus is just historically very important because I really think it's the first model in mathematics where programs, functions, and data were all swimming in the same soup, acting on each other without this strict hierarchy. Okay, anyway, so now that we've defined the lambda calculus, it does stuff with strings, but can we compute functions in it? What about functions in the integers? Well, we need to invent some encoding of the integers in the lambda calculus. And here's one convenient one, which are called church numerals, named after Alonzo Church. What we're going to do is think of the number n, the whole number, 0, 1, 2, or 3, as the function which iterates a function n times. So the 0 function is lambda fx dot x. What does that do? Well, you hand it any function and it ignores what function you were talking about, and it just takes the input x and hands it back to you. It iterates the function f 0 times and leaves the input unchanged. The number 1 would be the string which applies f once, 2 applies f twice, and so on. There are many ways to encode numerals as strings in the lambda calculus. This is just one that people like and find convenient. So nf applied to x would be f of f of f n times of x, f iterated n times.